Okay, this section's on continuous functions. You did continuous functions last year in tree, where you can draw the sine graph, and the general idea on continuity is if you can draw the graph without lifting your pencil, then it's continuous. If you have to lift your pencil and go to another part of the page, okay, then it's discontinuous. So we did a little bit of that, like last year, tangent graph would have been discontinuous because it went down through the origin, you had to lift your pencil. Okay, secant, cosecant, those would have been discontinuous. Okay, the first thing the author defines is continuity at an interior point. Okay. Continuity at an interior point. When they're talking about the interior point, they're talking about, like, if I showed you a graph here and I'm looking at, say, this interval from A to B, and they're talking about some point C in between, is this graph continuous? Okay? Continuity at an interior point C if the limit of the function f of x as x approaches C equals, and if there is a y value there, what would that y value be? Instead of f of x, what would it be? It'd be f of c, because your x value is c. Okay, so as long as there's a point there, okay, then it's continuous continuity at an interior point. Okay, then the author talks about continuity at an endpoint. Okay, if. Now, when they're talking at an endpoint, it would be like if they're looking at, okay, here's our, and maybe it stops, okay, and say this is our A and this is our B. Okay, what about at the endpoints? Okay, the limit of f of x as x approaches A. Now, when they put that positive side on the right, that says as it's coming in to the right, okay, as it's coming in to the right, they want to know what's this y value that it's approaching. And that y value would be f of A, because you're substituting A in for x. Okay? And you would also have the limit of f of x as x approaches B from the left side, and that should equal f of B, that y value. Okay, so you can read that section. That's just a little bit of their introduction. You're not just looking at the whole function, you're looking at the endpoints, you're looking at the interior points. Okay. Then the author defines a function is continuous. A function is continuous if its graph can be drawn without lifting a pencil. A function is continuous, okay, if its graph can be drawn without lifting your pencil. Like the sine graph that we did last year. Cosine is also continuous. Okay? Tangent, cotangent, secant, cotangent are not continuous. Okay? And that means a function is continuous at each point of its domain. Now, that means you got to look at division by zero and square roots of negatives. What is the domain for the function you're looking at? Okay, so that's their idea of continuous. Then the author talks about discontinuity. Discontinuity at a point means if a function is not, if a function is not continuous at a point C, then we say f is discontinuous, and this would be anytime you have to lift your pencil. It's discontinuous at C, and C is called a point of discontinuity. And then they have a little note here. Note, C may or may not be in the domain of F. And basically, anytime you have to lift your pencil, it's discontinuous. So you'd have a point of discontinuity if you have to lift your pencil. Okay. Now, I'm going to go through a graph, and every calc book will have basically the same type of graph for the continuity tests. Okay. The continuity test. F is continuous at x equals C, at x equals C, IFF, if and only if all three of these are true. Okay. Number one, the function f of C has to exist. That means if you choose an x value C, there's got to be a y value at that point. The limit of f of x as x approaches C has to exist. The limit of f of x as x approaches C has to exist. And the third thing, the limit of f of x as x approaches C has to equal the value f of C. If all three of those happen, then it's continuous at that point. Now I'm going to show you a graph and show you where some of these fail. Okay, on this graph, give me 4 tick marks on the x and 2 tick marks on the y. Okay, and then here's the graph. Put a solid point at 1 and at 0, 1. A solid open circle at 1, 0. Open circle down here and just a curve down to that point. Up here, put a solid point at 1, 1. And at 2, 1, put an open circle with a line in between. At 2, 2, put another solid point. At 3, 2, put a solid point and connect these two. Okay, and then at 4, 1, put a solid point and connect these two. Okay, now we're going to go through each x value, okay, and I'm going to show you which of these fail, okay? Okay, at x equals 0, on the endpoint there, okay, that would be a continuous point because it's defined. There would be a limit coming in from, on the endpoints it's only going to come in from one side. Okay? So that would be continuous. Okay? Look at x equals 1. First, is there an f of c at 1? Is there a y value at 1? Yes, it's 1, 1. So this is true, there is a solid point. Okay? Then you have to check number 2. The limit of f of x exists as x approaches c. Coming in from the left and the right, is it going into the same y value? No. This is the one that fails for x equals 1. So make a note, at x equals 1, number 2 fails. Okay, it's not coming in to the same y value. Because coming in from the left, it's going down to 0, that y value. Coming in from the right, the y value is 1. So this fails because it has to come into the same y value from the left and the right. So at x equals 1, number 2 fails. Okay, now let's look at x equals 2. Okay, go back to number 1. Does f of c exist at x equals 2? Yes, it's that point right there. Does the limit exist? Is it coming into the same y value? From the left, it's coming into 1. From the right, it's coming into 1. So the limit is 1. This doesn't have anything to do with the limit. Okay? So it's coming in to 1, so 2 is okay. Does the value of this function equal the value of the limit? Are those two y values the same? No. So number 3 fails. Make a note. At x equals 2, 3 fails. The value of the limit does not equal the value of the function. Okay, then let's check at x equals 3. At x equals 3, does f of c exist? Is there a y value? Yes. If you check the limit, if you're coming in from the left side, the y value it's approaching is 2. As you're coming in from the right side, the y value it's approaching is 2. Okay? Does the value of the function and the value of the limit, are they the same? Are they the same y value? Yes. So this one is continuous at x equals 3. Okay? It would also be continuous at that. There would be continuity at the end point. Okay? Okay, so that's how it has to satisfy all 3 of these for it to be continuous. Otherwise, you're going to have a point of discontinuity. Okay? Now, the author goes through 4 types of discontinuities. Okay, one is what they call a removable discontinuity. Here's an example of what a removable discontinuity would look like. I'm just going to make one up. Okay, a removable discontinuity is an open circle, basically. And if I could figure out what ordered pair would fill that in, that's why they call it removable. Okay. The second type of discontinuity is called a jump. A jump, like a step function would be a jump. If I said, okay, here's from here to here. Okay. It's like I've got to lift my pencil and jump up there. Okay. The third type of discontinuity is oscillating. Oscillating. And this is an example of an oscillating. Y equals -1. Put parentheses around that and raise it to the x power. Okay? if you look in a graph, if you did x and y, if you did -1 to the 0 power, sorry. If my x value was 0, I'd have -1 to the 0 power. What is -1 to the 0 power? 1. If you put 1 in, -1 to the first would be -1. Put 2 in, -1 squared, 1. If you put 3 in, -1. 4 in, 1. You can see these, it's just oscillating. 1, -1, 1, -1, 1, -1. Okay, now let's graph that so you can see what it looks like on the calculator. Put in a -1 and raise it to the x power. And I'm going to go zoom 6 to start. Now, your calculator may do that. Let's do zoom 4. See if there we go. Zoom 4 is a better window. Zoom decimal. And you should see just the dots. Put the trace key on. Okay. Now the bad part is it's got to go through the decimal places to get there. So if you don't want to do that, go zoom 8 and press enter for it to register. Ooh, I don't want that. Hang on. Let's see. Turn my axis off. Second function format turns that axis off, and we better go. Let's see if we go dot mode. There we go. Go dot mode. Okay, now put the trace key on, and it'll go right to them. So it's going 1, -1, 1, -1, 1, -1. Then you don't have to go through the decimals. Okay, so you're just going to end up with a graph, and it's just going to go back and forth. Okay, if x is 0, it's going to go up to 1. If x is 1, it's going to go down to -1. If x is 2, it's going to go up. If it's an odd one, it's going to go down. Even, it's going to go up. And it just repeats and oscillates. Okay, so that is a discontinuous graph. Okay, that's a type of discontinuity. And the fourth type you already had, you probably did it back in Algebra 1 and Algebra 2, and that was an infinite discontinuity. We did them infinite discontinuities in trig when we did tangent, cotangent, secant, cosecant, because they went to infinity. Tangent looked kind of like this, you know, and it repeated. There was an asymptote here, and it repeated. So that is an infinite discontinuity. Another example, like if you graph a hyperbola, you have to lift your pencil. Okay, so that's an infinite discontinuity. Okay. Okay. The next thing the author talks about is he asks a couple of questions. Draw a little separator there. What does it mean for a graph to be continuous? What does it mean for a graph to be continuous at every point of its domain? Okay, for example, if I gave you this equation, y equals 1 divided by x, what x values are not in the domain? X can't be what? When they say domain, you're worried about two things. You're worried about division by 0, square roots of negatives. I don't have any square roots in here. So x can't be what? Yeah, x can't be 0. So in the domain, your x cannot equal 0. Okay? And if you cross multiply, if we thought of this as y over 1 and cross multiply, you're going to end up with x times y equals 1. Anytime you have x to the first, y to the first, multiply together equal a number, it's always going to be a hyperbola. Okay, that goes back to your algebra 1. So if we graph 1 divided by x, and just go, let's go back connected mode, and let's go zoom decimal. Let's go zoom 4, zoom decimal. Whoops, I got to turn my axis back on. Okay, so you get a graph, okay, that looks something like this. You get a hyperbola that looks like this. Now, they're going to ask two different questions. Okay, say, is this graph continuous for every point in its domain? Okay, now I would ask first, where is this graph discontinuous? What x value is not in there? Or do you have to lift your pencil? At 0, right? So, is this graph continuous for every point in its domain? 0 is not in the domain. Is it continuous everywhere else? Yes. So the way they ask that question, it would be yes. Because 0 is not in the domain, that's the only place where it's not continuous. Now, if they reword the question, is this graph continuous over the set of real numbers? Basically, they're looking, real numbers are everything on the number line. Is this graph continuous all the way along here? No, it's discontinuous right there. So the answer is no. So it depends on how they word it. Okay? You've got to look at their wording. Okay. Put another little separator. The next thing the author talks about is compositions. All compositions of continuous functions are continuous. So, I'm going to give you an example. F of x, let that be the sine x. G of x is the cosine of x. Now, I'm going to, the last chapter I said for everything in this book, we always did 3 decimal places. Okay, this is another for everything in this book. Any trig function in this book, and the author's already told you in the writing, if it's a trig function, everything in this book is in radians unless they tell you otherwise. So automatically set your calculator. If you're doing the sine graph, you automatically go to radians. Okay, so clear out your calculators, clear out those equations. Make sure you're in radian mode. And if I wanted to do the graph for sine, remember I do sine, y equals sine x, and we have that zoom trig, zoom 7, and you should see the sine graph. Okay? And you could do the same thing for the cosine graph. Those are, sine is continuous, cosine is continuous. Now we're going to do the composition, and I'm only going to do one of them. I'm going to do f of g of x. Okay? So if I did f of, and I would put cosine of x in for this, g of x. Okay, so that's saying in the f function, everywhere you see an x, you're going to put in cosine of x. So you'd have, for this, you'd have the sine of the cosine of x. I'm putting that extra parentheses around the x just because the calculator will. Okay. So they want you to graph sine of the cosine of x. Okay, clear out that one. Graph sine of the cosine of x. What they're trying to get you to see is that this too is continuous. Okay? You can graph that whole graph without lifting your pencil. Okay, so draw a little sketch of that just to show you that it's continuous. Something like this. It's not the best graph, but it's to show you that this graph is continuous. If you have two continuous functions and you do a composition of them, your composition will always be continuous. Okay, now probably the most important part for the algebra part of this and for the test part of this is the section on removing discontinuities. Removable discontinuities are open circles. And this is how do you remove those discontinuities. I'm going to do it by an example. Say we have the function f of x, and up in the numerator is x squared plus x squared plus x minus 6, and down in the denominator is x squared minus 4. Okay? First thing you have to do is just like limits, factor it. Okay? Because you've got an x down in the denominator. If we factor the top part, there's nothing in common. What will that top part factor to? Plus 3 and x minus 2, right? And the bottom is the difference of two squares, x plus 2 and x minus 2. Okay, these two will divide out. Now, before we graph it, okay, you look at the denominator and you say x can't be negative 2, x can't be 2. Those are either open circles or they're asymptotes. Okay, go back and graph the original. Let's look at what the graph looks like. The author, you got to know to put parentheses around that top part. The x squared plus x minus 6. And then divided by parentheses x squared minus 4. Okay, let's do zoom 6 to start. Then we might have to change it. Yep. Okay. Here's your spike. Whoops. Ooh, hang on. So you should see a spike at should see a spike at x equals negative 2. Now, you might not see the open circle, okay, but your graph looks something like this. Sketch it. So at x equals negative 2, you got a asymptote, okay, and you've got a graph coming in. There's actually also one that's a horizontal. You guys don't know that much about these yet, but there is one that comes through like this. And the graph comes through this way. Okay? And at x equals 2, there is no asymptote, so there's an open circle. And you can double check it. Do second function calculate value at x equals 2. And you should have an open circle there. Now, here's what we're going to try to do. You cannot remove an asymptote, but you can remove that open circle by filling it in. Okay, now you could get close to it. Okay, you can get real close to it. Okay, as x gets closer to 2, okay, you can kind of look at your y value, and you might be able to guess. Okay, here's how you do it. Same way you did the limits. Star it, factor it, reduce it, sub in. Okay, so we factored it, we reduced it, those divide out to 1, and now you sub in. What do you sub in? You sub in this x value where the open circle is. Sub in 2. So if you put 2 in, 5/4 or 1.25, I don't care if you write it in fraction. If it's fractions, it's reduced, remember? So the ordered pair that fills that in is x equals 2 and 5/4. That is the ordered pair that would fill in that open circle. Okay? What you sub in is the x value. It has to be one of these two, not the one that's the asymptote. Okay? So when they ask you to remove a discontinuity, I can't tell you enough in Calc how many times you got to do factor it, reduce it, and sub in. Okay? Okay? Okay. That's as much as I'm going through on the notes on that section. Make sure you read that section.